There is a pattern hiding in the prime numbers. It was discovered on a napkin in 1958. Anyone with a calculator can verify it. 67 years later, no one has been able to prove it. Here is the pattern. Take the primes in order. Take the absolute difference between every adjacent pair. You get a new sequence. Apply the same rule again, then forever. Every row you produce starts with the number 1. The mathematician who first noticed this was a graduate student named Norman Gilbreath. He was doodling in a diner. He watched the leading one appear, row after row, and could not figure out why. We still can't. The pattern is rock solid through trillions of rows. The proof does not exist. This is Gilbreth's observation, and it has held up for 67 years. Write down the primes. Take the absolute differences. Take the differences of those differences. Take the differences again. No matter how many times you do this, 10 times, 1,000 times, 1,000,000 times, every row you produce begins with the number 1. The pattern is so easy to see that anyone with a calculator can verify it for the first 100 rows in an afternoon. The pattern is so reliable that no one has ever found a row that breaks it. The pattern is so stubbornly consistent that mathematicians took it seriously enough to give it a name. We call it Gilbreth's conjecture. And in 67 years, no one has proved it. That is the strange thing about this problem. It is not hidden. It does not require complex preparation to see. There is no abstract framework you need to understand before the question even makes sense. The question is, you write down the primes, you take differences. The leading number is always 1. Why? The honest answer is, we do not know. This video is about that question, about a doodle that became one of the simplest unsolved problems in number theory, about what it would take to actually prove it, and why nobody has been able to. Let us set up the doodle carefully. We are going to build what is called Gilbreth's difference triangle. Row 0 is the primes themselves, in order. To produce row 1, we walk across row 0 and take the absolute difference between each adjacent pair. This gives us a shorter sequence, sitting just below the primes. To produce row 2, we apply the same rule to row 1. Walk across, take adjacent differences, write the result below. Row 2 is shorter than row 1 by exactly 1 element. We keep going. Row 3, row 4, row 5. Each row is 1 element shorter than the row above it. The whole structure looks like a downward triangle, tapering to a single number at the bottom. That bottom number is always 1. So is the leftmost entry of row 2. So is the leftmost entry of row 3, row 4, row 5, row 10, row 10,000. The leading column of this triangle, all the way down, is filled with 1s. That is the entire conjecture. The leftmost column is a column of 1s forever. This is what Norman Gilbreath wrote on his napkin. And this is the conjecture. Every row of this triangle, forever, begins with 1. When Gilbreth circulated his observation in 1958, mathematicians did the natural thing. They tried to find a row that broke the pattern. Computers in 1958 were slow. They checked the first dozen rows by hand and stopped. Throughout the 60s and 70s, people checked deeper as computers improved. By the 80s, the pattern had held for tens of thousands of rows. In 1993, Andrew Odlyzko at Bell Labs did the definitive computation. He took the first 346 million primes, yes, 346 million, and computed the entire triangle they produce. Every single row began with 1. That gives you a sense of how deep the verification goes. The triangle reaches more than 300 billion rows deep. Every one of those rows starts with 1. No exceptions, no outliers, no row that almost works but ultimately fails. The pattern is rock solid. More recent computations have pushed even further, into trillions of rows. The pattern holds. In number theory, this kind of empirical confidence is unusual. For most conjectures we have, we can prove that they hold for small cases, and we believe they hold for all cases. For Gilbreth, we have verified more cases than any human will ever look at, and we still cannot turn that into a proof. The data is overwhelming. The proof does not exist. If you spend more than 5 minutes looking at the Gilbreth triangle, you notice something else. The rows are mostly zeros and twos. The first row is the original prime differences. Those are larger, 2 and 4 and 6 and so on. But after a few rows, almost every entry in every row is either 0 or 2. Occasionally a 4, occasionally a 6, but mostly zeros and twos. This is not just a visual coincidence. The mathematical reason is straightforward. The first row of differences is even, because primes after 2 are odd, and odd minus odd is even. From the second row onward, every entry inherits that parity. Differences of even numbers are even. So the entire triangle is even from row 2 onward, except for the leading entry of each row, which is the mysterious one. So after a couple of rows, you are working entirely with even numbers, and the differences of even numbers cluster around 0. After enough operations, almost everything is 0, with occasional 2s popping up to keep the row from collapsing. This is part of why the conjecture is so hard. The triangle is, in some sense, very simple. It is a sequence of mostly 0 rows. Saying that the leading entry of every row is 1 feels like it should follow from this simplicity, but it does not. We can prove the rows are mostly zeros and twos. We cannot prove the leading entry is 1. Here is the most surprising twist in this whole story. In 1993, the mathematician Hallard Croft made an observation that changed how people think about the conjecture. Croft pointed out that Gilbreth's pattern does not actually depend on the primes very much. It depends on the fact that the primes have a specific statistical character that is shared by many other sequences. Specifically, take any sequence of positive integers whose first row of differences is all even except for the leading one, and whose entries do not grow too fast. You will get the same Gilbreth behavior. Every row of the difference triangle will start with 1. This is a strange result. It means that Gilbreth's conjecture, despite being stated about the primes, may not actually be a fact about the primes at all. It may be a fact about almost any sequence with mild generic properties. The primes are just one example. This is supposed to be reassuring. If the conjecture is generic, the proof should be generic too. We should be able to prove it without using any deep facts about the primes. We should just be able to prove a clean combinatorial statement about sequences of integers. So mathematicians tried. They tried to prove it for general sequences. They tried to prove it under the mildest possible assumptions on the input sequence. None of these attempts succeeded. The leading entry being 1 resists every approach. The conjecture is not about the primes. The conjecture is about a structural pattern in difference operators, and we still cannot prove it. So why does this problem resist proof? Let us be honest about the difficulty. There are unsolved problems in number theory that mathematicians know how to attack. The Riemann hypothesis has dozens of partial results. The Goldbach conjecture has Vinogradov's theorem, Chen's theorem, sieve-based progress. The twin prime conjecture has Zhang's bounded gaps result. These are problems with handles. Gilbreth's conjecture has no handles. There is no partial result. There is no sieve method that produces a weaker version. There is no analytic approach that gives any quantitative bound on the conjecture. The literature consists essentially of computer verification and Croft's heuristic argument about why it should be true. Why is it like this? Because the leading one property is too local. It is a statement about a single entry in each row. The mathematics we have for studying difference triangles is much better at proving things about averages, or about typical behavior, or about asymptotic density. It is much worse at proving things about specific individual entries. The leading one is a specific individual entry. The problem and the available tools do not match. We need new tools, or we need to find a hidden structure that nobody has spotted yet. 67 years and counting, neither has happened. Let us enumerate what is genuinely open. We do not know whether Gilbreth's conjecture is true. We believe it is, the evidence is overwhelming. But belief is not proof. We do not know whether the leading one is something special to the primes, or something general about all dense enough sequences. Croft's argument suggests general, but Croft's argument is heuristic, not rigorous. We do not know whether the same pattern holds in higher difference operators. If instead of taking the absolute difference, you take the difference of differences, or some weighted combination, does the leading one pattern persist? Numerically, sometimes yes, sometimes no. There is no theory. We do not know whether a counterexample, if one exists, would appear at some astronomically large rho. The empirical evidence rules out anything within reach of current computation. But there are conjectures in number theory that are true for the first 10 to the 20 primes and fail somewhere beyond. We have no way to rule this out for Gilbreth. We do not know what would constitute a proof. No one has identified a structural property of difference triangles that would, if proved, imply the leading one pattern. There is no roadmap. Norman Gilbreath died in 2022. He never proved his conjecture. He never expected to. He was an applied mathematician, not a number theorist. The doodle was a curiosity, not a research program. But the curiosity outlived him. The napkin from a 1958 diner has become one of the simplest open problems in mathematics. Anyone can understand the statement. A child can verify the first 10 rows, and no living mathematician knows why the pattern holds. This is what makes Gilbreth special. Most unsolved problems in mathematics are technical. You need years of training to understand the question. Riemann, Birch and Swinnerton-Dyer, Hodge, these are deep and abstract. You cannot explain them to someone over coffee. Gilbreth is different. The statement is, write down the primes. Take the differences. The leading entry is always 1. Anyone can see the pattern. Anyone can verify it. And nobody can prove it. That is the strange beauty of this problem. It is not waiting for some new branch of mathematics to be invented. It is not waiting for a tool from algebraic geometry or arithmetic dynamics. It is, by all appearances, an elementary statement about sequences of integers, and it has resisted 67 years of effort by people who are very good at proving things. What did Norman Gilbreath see, exactly? He saw a structure that is real, that is verifiable, that is consistent across more cases than any human will ever check. He saw it on the back of a napkin, and the rest of us have not yet figured out why it is true. A diner, a napkin, a 15-minute doodle, and one of the prettiest, most stubborn open questions in number theory.